Okay, we're starting. Before we get into the main topic of today, just some housekeeping. I think in haste I probably made an error in the last problem we did yesterday. So I just want to make sure, I didn't rewatch the video yet. You might have noticed it's not posted. So I just want to make sure I actually wrote down the alternative thing correctly. So let's just go over that. You might have recall this is L goes from P2 to P2, where L of P is just going to be 2 times P minus 3P prime. And A was to find P of B if this is the polynomial 5 minus 6t plus 4t squared. B was to find the standard matrix of L with respect to the basis B, and C was to compute L of this guy with respect to the matrix, with respect to the basis B, where B was a basis for P2, which was 1, 3t plus 1, 2t squared. Okay. So the first time we went through this, that was correct, I believe. But I want to know, as the alternative to our solution. Right, the version basically using transition matrices, how do you get that one to work? So either one is annoying, but you might find one less annoying than the other, so I want to give you a couple options here. So an alternative to A, to actually find this guy, he's expressing the standard basis. I want to express him in terms of the basis B. We could do a transition matrix. From the standard basis to P of B. So you might want to do that. And that would involve, of course, computing this thing. This is 1, 0, 0. 1, 3, 0, 0, 0, 2, which is just expressing this basis in terms of coordinates using our typical mapping. And then we put the standard basis on this side. So this is the old basis we want to translate to the new basis. And so by doing that, we get I3 on this side. And on this side, you'll get this guy, 1 minus a third, 0, 0, 1/3, 0, 0, 0, 1/2. And so this guy here would be your transition matrix from S to B. And so now how you actually use that to find A. So now that just means to write this guy in terms of B, just take that transition matrix, P from S to B, and multiply by the P. And so that would mean taking this matrix, 1 minus a third, 0, 0, 1/3, 0, 0, 0, 1/2, multiplying that by the standard matrix for this, which is 5 minus 6, 4. So this is in the standard basis. This transitions from the standard basis to the basis B, and that would actually give you the 7 minus 2, 2. So that's an alternative to part A. You're right, you still have to do some row reduction, but instead of jumping around, you can just do it in one fell swoop. Okay. For part B, we could have done is to realize that the standard matrix for L would just be this right? Would just be L of these basis vectors, which is 1, 2, 0, L of 0, 0, 2. That would be the standard matrix. Now this one, it was a lot easier to find because we could just use the calculus interpretation and get to these pretty quickly. And we actually did that. And we found that this was 2, 0, 0, minus 7, 6, 0, and 0, minus 12, 4. And then we can do another transition matrix to get the answer to B. So if we transition from that thing that we just created to this guy, when we reduce that, we would have gotten the answer to B. This is 2 minus 9, 4, 0, 2, minus 4, 0, 0, 2. That would give us in terms of the basis B. Now, of course, you have to write out the details here. I'm just giving you an outline for the proof. You have to do this. And C, we would do the same thing, essentially. There is an alternative way to get C done. Let me just write that down. You could either do the same thing as we did last time, or I'll give you an alternative. First one, this guy, which will be 28 minus 36 and 8. Right? So you just take the polynomial, take 2 times the polynomial minus 3 times its derivative. You'll get these are the coefficients for the polynomial. And then to find that guy in terms of B, again, just do the transition matrix that you found from part A and multiply by that. And that will give you the answer that we got to part C last time, which was 40 minus 12 and 4. And these are using the theorems that we covered in 4.6 and in chapter 8.4. So it's a combination of the two. So there's more than one ways to skin a cat. Those are 2 alternative ways to solve that problem. A problem like this will be on the final and on test 2. Which, speaking of test 2, a little bit more housekeeping. Let's talk about what that's going to look like. Again, 6 problems and 1 bonus. So 6 that you have to do, and there will be an additional bonus problem that is optional. Here are the kinds of things that you should be expected to do. Hopefully you've already been studying, but make sure that you focus on these and you know how to do this. And So the first thing you need to know how to do is things like this. Know how to change bases, find transition matrices, and use them to find coordinates with respect to some basis. So it's kind of like we did some examples in 4.6 as well as examples like these from 8.4. So if you can look back at those lectures and see problems like of that type, you'll have one. I'll ask you to prove some subsets are subspaces. So know what it means to be a subspace, and I'll give you specific examples. I'll tell you about a vector space, and I'll describe a subset of that vector space, and your goal is to prove whether or not it is a subspace, right? So you should remember you should need to verify two things for that to happen. So it will involve some sort of proof. There will also be some sort of proof involving properties of linear transformations. And those are the general kinds of proofs, so that things like is something one-to-one, or is it onto, or if you know it's one-to-one, does it imply this, or if we compose two of them, what properties that has. So the general properties, so basically the kind of things we talk about in class, know how to prove those properties. So things like knowing that the kernel is trivial, can you prove that the linear transformation has to be one-to-one? Things like that, or maybe similar properties to that. All right, so the basic generic properties. So for this one, I'll give you some specific example that I want you to work through, but it still involves you writing a proof. The proofs in problem 3 is the generic one. So if you know two linear transformations are one-to-one, show that their composition is one-to-one. Or if you know both are bijective, show that they're bijective. Or I could say, given that T1 is a linear transformation and T2 is a linear transformation, prove that the composition is also a linear transformation. And you need to be able to prove things like that. So the very general properties here is what I'll ask. 4, I'll ask you to find bases for like the row space, column space, null space of a matrix. Also to talk about the rank and nullity and the dimensions theorem for matrices. So know what the rank means, how to find it, what the nullity means, how to find it, and their relationship, which is given by the dimension theorem. Proofs about linear independence. So that would involve examples like, okay, if you know there's a finite set where all the vectors are linearly independent, then every subset of it is linear independent, things of that sort. So again, specific example about linear independence. So you obviously need to know what it means to be linearly independent, and vice versa. So I might include span here, but I'm pretty sure I'm going to ask about linear independence, but know about span. And then linear transformations, as in specific problems about linear transformations. So I'll tell you a transformation and I want you to figure some things out. So know how, given T, some linear transformation, can you find its standard matrix? Can you find its inverse? And how do you know that it exists? So I give you a random linear transformation that does something. Can you find a matrix that describes that transformation? Is that matrix invertible? How would you know that an inverse function exists? What would you have to check? Things of that sort. So those will be the 6 problems. These 2 are computational. right? So they both would involve you doing some row reduction. The rest, though, involve you doing some sort of argument. Okay? So you need to know what makes a subspace. Right? There are two things you have to check closure under: addition and scalar multiplication. And you need to know what it means to be linear independent, what it means to span a set. And so determine whether or not a set I give you is linearly independent, and proofs that might arise from there. Know about some general properties of transformation, how to prove them. It's the kind of things that I would have mentioned or proved in class, as well as given some specific transformation, I can tell you what it does. Can you find its matrix? Can you find its inverse? How would you know the inverse exists or not if you're not even required to find the inverse? That sort of thing. The bonus would be on what we're going to do today. So I'll also put a bonus on eigenvalues, eigenvectors, basically how to compute them. It's going to be a very computational problem. Diagonalization, solving systems of ODEs. Linear ordinary differential equations. So this is basically what we're going to cover today, and I'll put that as the bonus. It's going to be very computational.
How many points are there? Is the bonus?
Same. Together, this will come in like several parts, maybe, so 20 points. So 100 points from here, 20 points from there. And you have to attempt these in order to do those, but that's the basic outline. Let's move on now to the topic of the day. Eigenvalues and Eigenvectors. And just throw the definition out there. Definition. We'll talk about it. Let A n by n be a linear transformation. So we're going to take the geometric point of view for the most part. So that's kind of the picture I want you to have in your head. But there are a lot of non-geometrical applications, and we'll discuss some. A non-zero vector x in Fn is called an eigenvector of A if A times x equals lambda times x, where lambda is a scalar, it's in your field F, and hopefully it's not 0. I mean, it could be 0. There are theorems where we care about it not being 0. And by the way, lambda is called the corresponding eigenvalue of x. Let me write it down in a little bit less technical language, and then we'll talk about what that means. i.e., the set of vectors that are only scaled by a linear transformation are its eigenvectors. The scaling factors are the eigenvalues. So we looked at geometric, the idea that, let's say we're in R2 or R3 for easy visualization purposes, I can hit it with a matrix and it will change vectors in that space. I can do a rotation matrix, I can do a projection matrix, and we are concerned with the matrices, with the vectors in our space, that when I hit it with the linear transformation, it doesn't radically change it. It will remain on the same path, but it may or may not be scaled. Okay? So if I look at something like, example, if I look at projection to x-axis, right? In R2, that means your A looks like this, 1, 0, 0, 0, right? So that linear transformation does what? Like if you have any vector, it will just drop it down here, right? It'll project to the x-axis, right? So this is our vector x, right? Now if your vector x looks like this, by definition it is not an eigenvector, right? Because it literally changed its direction. It's not parallel to what it was before, right? So when I multiply it by this matrix, it's not a scalar multiple of itself. It's not parallel. However, any vector along the x-axis, hit it with this, it's not going to change at all, right? It's going to maintain its direction, right? In fact, it's going to be scaled by 1. So any vector, under this transformation, any vector that is parallel to the x-axis is an eigenvector, and their eigenvalues will be 1. Right? That's one way you can think about it. Also, technically, any vector that's directly perpendicular to the x-axis, when you boom, hit it down, technically it's a scaled version of itself. It will be a 0 scaled version of itself. That will have eigenvalue 0. So all the guys that, when you, under a linear transformation, they're only scaled versions of themselves. They might be stretched or shrinked. You might reverse their direction completely in a 180-degree fashion, but as long as they don't completely change their direction, we call them eigenvectors. And the scaling factor is called the eigenvalue.
So the eigenvector only applies to horizontal vectors? Or
no. In this particular example, it applies to things that are horizontal and vertical.
okay.
Because the thing is, if I take A times X, what it does is it projects it to the x-axis.
Always, or just in this case?
In this case, I have to be mentioning this, I have to tell you what the transformation is. You're not going to know. It's not. It will change from different transformations. So I can give you a linear transformation, tell you, here's a matrix, think of it as a linear transformation, what are its eigenvalues and eigenvectors? So you look at that matrix and you want to figure out if what vectors in my vector space will only be scaled by this matrix. Here's another example. Suppose I have a linear transformation going from the differentiable functions to the differentiable functions, and where A is the differentiation operator. Then, any function that has this form, e to a constant times x, is an eigenvector with eigenvalue k. Since if I apply a to this function, that means take the derivative, the result will be k times that function. So I apply my linear transformation, the result is a scalar multiple of the original, right? So any function of this type will be an eigenvector, and the scaling factor will actually be the coefficient of the power. So that's another example. So you can apply it to functions as well. Any vector space can have these things. Okay. I'll give you a specific example here. I is an eigenvector here, whereas the vector 1, 1 is not. since under this transformation, I is not going to change. It's going to be scaled by 1. However, this guy will completely change his direction. He started out moving at a 45-degree angle to the origin. He ended up moving at a 0-degree angle to the origin. He completely changed his direction. So we only care about the guys that are being scaled by our linear transformations and not necessarily fundamentally changing their behavior. Finding eigenvalues and eigenvectors are important, right? Very important. Right? Those of you who have taken differential equations, you've seen applications of this before. The solution to the heat equation, for example, you are actually finding eigenvectors of a linear differential equation. Right? So the solution to the heat equation came from you searching for eigenvalues, which are differentiable functions that are scaled by some differential equation. Right? So that way you could figure out the heat distribution in a rod with insulated ends. So that's one engineering application. We'll use applications that are very mathematically focused. So finding these guys can help us diagonalize a vector. That means write it as a diagonal vector. And diagonal vectors are easy to work with, right? Their determinants are just the product of the guys on the main diagonal, and we can find their inverses by just inverting the guys on the main diagonal if they're non-zero. So that's going to be very useful. We can use it to actually solve differential equations, systems of differential equations. We're going to do that today as well. But there are many important reasons for this. And in a higher level linear algebra class, you'll learn a lot more important ideas from this. To take something from a real world example, I don't know if any of you checked out that link that I posted in the syllabus about the search engine. But basically, the thing that made Google the preeminent search engine when it was born is this. The fact that the Google search engine actually used eigenvectors and eigenvalues to do in page ranks. Basically, they rethought of a matrix as, basically they thought of a graph, right? Right? Which, I don't know, some of you might have done some graph theory and that sort of stuff. You might have seen this in combinatorics, maybe in a discrete math course, maybe you've done graph theory otherwise. But you can think of a graph, and basically all these points here are certain websites. So they're like, okay, the internet is just a connection of websites. They thought of it that way. Then they pretty much put in a matrix where each website gets an entry in this matrix. And that matrix encoded the probability of someone clicking on that website when they search for a particular term. And so now the question is, which ones will have the highest probability? And those will get a higher rank. It turns out to actually answer that question ended up being an eigenvector problem. Finding the eigenvalue of this vector, which by the way, it's a vector that collects websites on the internet. So it's a huge matrix. You can't actually do this by hand. But the foresight to be able to see that and tell the computer, here's how I want you to rank pages. Set up this matrix, find those probabilities, and find the eigenvector and eigenvalues, and then rank the guys with the largest values. And those will be the most relevant websites. Those are the websites that people check out the most often, and they stay on them, right? So the Google search engine, in its early stages, was an application of eigenvalues and eigenvectors. So with a little creativity, so a lot of people, they go through school like, oh, how am I ever going to use this in my life? You know, why do I need to know their parallelogram? With a little creativity, all the things, if you just re-envision your world in terms of the mathematical objects we're using, you can get to all sorts of nice results. But that's a very quick oversimplification of how Google works, but that's essentially how it works. It tracks website relevance by matrices of probabilities, and the highest probabilities are determined by eigenvectors. So, that being said, let's actually say, how do we find these? so basically, we need to solve I want to know what vector x's solve this equation. We need to solve this for x. And I want my vector, of course, x to not be 0 because that will just be silly. Of course, the 0 vector is going to be scaled by any linear transformation. That's a trivial amount of information I don't need. So essentially what we can do is to say, hey, let's subtract this from both sides. We're in a vector space, we can do that. We can also factor out the vector x. And so basically what happens is we want non-trivial solutions to this. How can you ensure that that has a non-trivial solution?
No.
Right? Think of this as like, it's just some other matrix, right? It's a difference of matrices.
Oh, non-trivial? You want linear?
I want non-trivial solutions. I want the guys that are not 0 that solves that equation.
That matrix has to have a determinant of 0?
No inverse?
No. Literally the opposite. The determinant must not be 0.
Yeah, one of them.
Because
You want to be linearly dependent, right?
we want to be dependent, so the determinant must be 0. Right, so this means the determinant of this lambda I must be 0.
What?
Right? Why the equivalence theorem, right? We know that if bx equals 0, if the determinant of b equals 0, then this has a unique solution, which is going to be the trivial solution. We don't want the trivial solution, so I need to make sure, if the determinant is not 0, we have a unique solution. I don't want that, so I just force the determinant to be 0, and then I don't have a unique solution. I will have many solutions. So that is how we want to find it. By the way, this is the same. I like doing it this way. It's not going to matter. This is the same as just saying, putting this the other way around. Because you're just going to end up with a polynomial in either case. I like to solve it in this direction. But it's really not going to matter. So, the lambda that make the determinant of lambda I minus A equals 0 are eigenvalues. To find their eigenvectors, solve for each lambda that equation. So by doing this, I can figure out the lambdas that will work. I just need to find the lambda that makes this 0. Once I do that, plug that lambda back in here and solve that, and that now will just be a system of equations. I can solve for the x. So to find the eigenvectors, solve for each lambda the equation lambda I minus A times x equals 0. Let's actually do an example, specific. Example. Find the eigenvalues and eigenvectors. So here I'm giving you a linear transformation. I'm going to give you a 2 by 2. So it's a transformation from R2 to R2 is one way you can think about it. Right? So that's a transformation that will do some sort of manipulation of R2. And I want to know what vectors in R2 are only scaled by this linear transformation. So this tells us how we're going to do it. So step 1, set the determinant of lambda I minus a equal to 0. Okay? Now you don't have to start here. I'm going to show you at the point where you can start. So what this means is you want the determinant of, this is lambda times the identity, so that looks like this, lambda 0, 0, lambda, minus the original matrix. I want the determinant of that matrix to be 0. This means this is the determinant of lambda plus 5 minus 2 lambda plus 2. I want the determinant of that matrix to be 0. Right? Now ultimately you can kind of jump to this step. Right? So this, so you just take basically lambda minus this, take the negation of that lambda, just take lambda minus everyone on the diagonal, and then change the sign of everyone else, and that gives you the matrix that you have to find its determinant and set to 0. What's the determinant of that matrix?
Lambda plus 5 times lambda plus 2 minus 2.
Lambda plus 5 times lambda plus 2 minus this times that, 4 equals 0. And so now this is just a polynomial. So this is just lambda squared. This is 5 lambda, that's plus 7 lambda. That's 10 minus 4 plus 6 equals 0. So it turns out to find the eigenvalues, I need to solve that polynomial equation. How do we solve this equation? We try to factor it. So if you remember algebra here. So 6 and 1. And what do they have to be? Positive, both of them. Right? So this means I have one value is minus 6, another value is minus 1. So these are my eigenvalues. So those are the scaling factors. Now let's find the eigenvectors. Alright, so I give you a matrix. Find lambda I minus that matrix. That's a new matrix. Find the determinant of that, set it equal to 0. That ensures that you will have non-trivial solutions and you will get the values. You would end up solving some polynomial. Clearly an n by n matrix, you will have to solve an nth degree polynomial. So this is a 2 by 2, so you end up with a quadratic. If it was a 3 by 3, same process, you'd just end up with a cubic that you have to solve. And probably on the final I'll give you a 3 by 3, but on test 2 I'll just give you a 2 by 2. So practice both variations. But the process will be essentially the same. It's just that when you get here, to find the determinant of a 3 by 3, you might have to use something else. But that being said, now things correspond. So it's important that you keep track of who is dealing with who. So let's go for if lambda 1 equals 6, minus 6, we need to find the eigenvector. So what I'm going to do is I'm just going to plug that in into the big matrix, which I want to be equal to 0, right? So I know I want lambda plus 5 minus 2 and minus 2 lambda plus 2 times x to be 0, i.e. plug in the lambda. If I plug in minus 6 here, what do I get?
-1.
Minus 1, minus 2, minus 2, plug in minus 6 here. I get minus 4 times x equals 0. Okay? This guy, I can just augment. how do we solve that system?
The second row is a scalar multiple of the first, so we get a
Okay, so I can just do 1, 2, 0. That's just row 1 times minus 1. And the second one is actually a multiple of this. If I take row 1 minus, we'll take row 2 minus 2 row 1, right? Then that gives me 0, 0, 0. Right? And you should always get a row of zeros because you should have a non-trivial solution. Now what we have, you have to remember how to solve these equations. So here I would set x2 equals t. So my x1 is just going to be minus 2t. So this means my x looks like minus 2t, t, which give me t times minus 2, 1. So this guy, what you can call these, everything. These are the Eigenvectors corresponding to lambda 1 equals minus 6. In other words, what I'm saying is, under this linear transformation, every vector that is parallel to that vector will be scaled by a factor of minus 6. Right?
It's excluding when t equals 0, right?
Well, 0 itself is also scaled technically. We care about the non-zero ones, but it would involve 0. It would involve 0, it's just that we don't get any information from it. Right?
Okay.
It's not the thing we care about. Scaling 0 by anything just gives you 0. Whoop-de-doo, no information. But if I know the vector minus 2 comma 1, knowing that that is flipped and then stretched by 6, that's important information. Okay? And any vector parallel to that will be scaled by this value. Let's go for the other one. What if lambda, so now we look at the eigenvector for lambda 2.
Professor? You
Yes.
said the second row has to be all zeros because they're non-trivial?
We want the non-trivial
Okay.
solution. Because our definition is the vector has to be non-zero. But if it's not a row of zeros, you'd have the identity here, and that gives you the 0 vector, which is like, we don't want it. So now you go for lambda 2 equals minus 1, was it? Okay, so now what you're going to do is you're just going to solve that new system, plugging in minus 1 for lambda. So if you plug in minus 1, you get 4. Plug in minus 1, you get 1. And by the way, I'm expressing this here, but you could just start here. You don't have to write everything out. I just wanted to write it out the first time I'm doing it. So just keep this matrix in mind and remember that you're plugging in the lambdas in here. And you need to solve for the x value that gives you 0. So end up here, and what would this do? I can do something like 2 minus 1, 0. This is row 2 times minus 1. And then I can just take row 1 plus 2 row 2. And that would give me 0. Have a row of zeros. Similarly, x2 is t. And so my x1 would be t over 2. And so this would mean, in this case, my vectors would be t over 2, t, which is t times a half, 1, which I can just take some other scalar, something like, instead of t, take 2k and scale it to be that. And these here are eigenvectors corresponding to lambda 2. So that random linear transformation I just gave you, you hit vectors in the plane with it, it's going to do something to all the vectors. 2 directions in particular will only be scaled. Vectors that are moving in this direction will be scaled by minus 6. Vectors moving in this direction will be scaled by minus 1. All other vectors will fundamentally change their directions, except the 0 vector.
Wait, so like, do some people consider the 0 vector as an eigenvector?
No.
It's not random.
The definition usually says we're assuming the vectors are non-zero.
Non-zero. So the other one and this one, k can't be zero then, right? So
Yeah,
you're-
we exclude zero.
Okay.
Technically, zero is an eigenvector. It's just the trivial one. It's the kind of one that, yeah, it's true, but we can't do anything with it. So we're searching for the non-trivial ones.
Sorry, I missed that last part. What was the translation from T to K? That mapping? I just.
So we're going to ultimately want to do things with these. So deal with fractions might be
Okay,
annoying.
so you just converted it to.
So I just wanted to convert it to whole numbers, so I just multiplied by some
I see.
LCD.
Okay.
We can do that here because
Parallel.
and it's parallel.
Right.
So there's an example. That is how you would find one. So I give you a matrix, take lambda I minus that matrix, find the determinant of that, set it equal to 0, you'll get the eigenvalues. Once you get those, plug them back into that original equation and solve that equation. The vector solutions corresponding to each one, that's how you find the eigenvectors. So that was a fully worked out problem. Yeah.
Is there any connection between the eigenvectors? That you find?
You mean these?
Yeah.
Not directly, no. There are connections between these and other properties that we're going to be talking about. So I'll just write the answer here as a summary. So we have lambda 1 equals minus 6 and lambda 2 equals minus 1 are eigenvalues of A, the specific A that I mentioned at the beginning of this problem. Lambda 1 vector is an unofficial notation, but I just like, for me to keep track of who corresponds to who, that's important, is going to be minus 2, 1, and my lambda 2 vector is going to be 1, 2. With the understanding that anyone parallel to these guys is also going to be scaled by the same. So in this linear transformation, any vector parallel to these two will be scaled by these two respectively. All other vectors will fundamentally change their direction.
For the second one, you don't have to write the k anymore? For the,
No,
no?
you can take it or leave it. There's an understanding that anything parallel to these will work. So you can throw it in or not, I don't particularly care.
So that's like a basis set then, right?
Yeah. In fact, that's what I'm saying. Further, we can talk about the eigenspace, and these would form a basis for the so-called eigenspace. And knowing the eigenspace of a matrix has a lot of theoretical implications. We're not going to get too much into that, though. We are more concerned, in chapter 5, we're very concerned with very computational things. Computing these guys, which is just solving systems and determinants, as well as using them to diagonalize matrices and solving systems of ODEs. That's what we care about. But there's a whole, from this would be the point where elementary linear algebra ends and real linear algebra begins. You start exploring things like this. So 5.2 is diagonalization. So here's a definition. A, B are matrices. They are called similar if A equals P inverse B, P for some invertible matrix. So we start with the definition of similar matrices. This is saying A is similar to B. And you can note it's of course symmetric. If A is similar to B, then of course B is similar to A. Because P is invertible, I can multiply both sides. I can move the P's on the other side and I get the same relationship. So, basically, here's the definition. A is called diagonalizable if it is similar to some diagonal matrix. These guys are n by n, by the way. They're square matrices. Which a diagonal matrix is also a square matrix. Okay? Which means if we can find a diagonal matrix such that A is equal to some matrix on this side, the inverse of some matrix here, and a matrix on that side, and in the middle there's a diagonal matrix, we call A diagonalizable. So, i.e., A is diagonalizable. If there exists some diagonal matrix D and invertible matrix P such that A would be the inverse D times P. Right? Now remember, a diagonal matrix is the guy where if you're not on the male diagonal, you are 0. And P is said to diagonalize A. Now here's the theorem. Let A n by n be a matrix the following are equivalent. 1. A has n linearly independent eigenvectors. Right? So find all the eigenvectors of A. If they're all linearly independent and you have n of them, A is diagonalizable. So you can write A in this form. Some matrix times the diagonal matrix times the inverse of the first matrix. So we can use eigenvectors to determine when a matrix is diagonalizable. Moreover, we can do better than that. I can tell you exactly how to do it. If lambda 1, lambda 2, up to lambda n, you don't have to have n eigenvalues. let's say with multiplicity, are the eigenvalues of A with multiplicity and lambda 1, lambda 2, over to lambda n, not with multiplicity, are linearly independent corresponding eigenvectors, then, right, so I found n eigenvalues, perhaps with multiplicity, I can repeat them, right, so that's if your polynomial has repeated roots, that's possible. Still just line them up, make sure you line up the vectors in the same order, right? So if I know a matrix has n linearly independent eigenvectors corresponding to these eigenvalues, I can tell you exactly what matrices will diagonalize A. Then P equals lambda 1, lambda 2. Take the eigenvectors and put them as columns in a matrix. That will diagonalize your A. And the result is going to be the corresponding eigenvalues along the main diagonal. Which is pretty nice, pretty cool. So if I can find the eigenvalues and eigenvectors, which is no more complicated than what I showed you before, assuming that we have n independent eigenvectors for an n by n matrix, that matrix will be diagonalizable, if and only if we can do that. On top of that, these are the matrices that gets the job done. Take all the eigenvectors, throw them in as the columns in a matrix, and make sure they correspond to the diagonal entries. So its eigenvalue would be in the 1 by 1 entry, its eigenvalue would be in the 2 by 2 entry, so on and so forth. The eigenvalues will line the diagonal of the diagonal matrix, and the eigenvectors that correspond to each one will be in the columns of the matrix that diagonalizes A. So let's actually do an example. Let's piggyback on the last example. I think that's what I did. So, example. A equals minus 5, 2, minus 2 minus 2. We found that lambda 1 is minus 6, lambda 2 is minus 1, lambda 1 vector is, what do we have? Minus 2, 1. Lambda 2 vector was 1, 2. Then set P equals this guy and D equals this guy. So literally take this vector, put it as the column. Minus 2, 1. Take this vector, put it as that column. 1, 2. Take the vector, the eigenvalue corresponding to this, put it here. Take the eigenvalue corresponding to this, put it here, 0 here, and 0 here. These diagonalize A. Because these two vectors are linearly independent, you can check for yourself, i.e. A is equal to this matrix times this times the inverse of that. And you can actually compute that. When you can compute these, and you will get the result minus 5, 2, 2, minus 2. We're not proving it, I'm just telling you that's what it's going to be. I actually wrote out what this was, so maybe I should. If you want to take the inverse of this, it's going to be minus 2 over 5, 1 over 5, 1 over 5, 2 over 5. So you can verify this just in case you're not sure, you want to check if you made a mistake. But in general, if I ask you to diagonalize a matrix, you can stop at this point and tell me, oh, these are going to do it. Right? So putting the eigenvectors in columns will diagonalize the matrix, and the diagonal matrix that pops out will be the one where the eigenvalues corresponding to each column are on the main diagonal. It's pretty nice. So that's one application, yeah.
I thought you said the inverse was on the left. Did I have to copy that down?
No, when we're diagonalizing it, it's on the right. Technically, it doesn't matter because this one's the inverse of that one. But it works in this order.
I did copy it.
Yeah, the inverse should be on the right. It will work in this order. Because matrix multiplication is not commutative. If I put it in the other order, I'll get something else.
Just the eigenvectors times the eigenvalues times the inverse of the eigenvectors.
This is a matrix where the eigenvectors are the columns.
Yep.
And so this is an eigenvector.
Yep.
It corresponds to the first eigenvalue. And then this one corresponds to the second eigenvalue. So these are the eigenvectors here, these are the eigenvalues here. It has this relationship. And if you actually do this computation, take P times D times P inverse, you can simplify that, you'll get to A. So again, that's something you should be able to do. So I can say something like, here's a matrix, find its eigenvalues and eigenvectors, and diagonalize A. Right, and then this would be the additional step you take.
When you say diagonalize A, you mean,
Write it in this form.
okay, just write it in that form?
Yeah.
Okay.
So you can say that, or you can tell me this matrix diagonalizes A, and this is the diagonal matrix. So here, this is the diagonalize A. So you're writing A as some matrix times the diagonal matrix times the inverse of that matrix. So, why is this useful? I mean, it's nice, it's neat. Is it useful? It turns out it is useful. For one, remember diagonal matrices are easy to deal with, right? In terms of finding determinants, which we know are important, in terms of finding inverses, lots of things. They're much easier with diagonal matrices. And again, that's nice, but why is this useful? So, also, if we consider P inverse AP, right? Which, notice that this is the diagonal matrix, right? So if A is equal to P times D times P inverse, then I would be able to solve for the diagonal matrix and write it like this, right? Now, what are some important? It turns out has many of the same properties as A. It has the same rank. It will have the same nullity. It has the same eigenvalues and eigenvectors. Has the same eigenspace. has the same, a whole bunch of things that we really care about with matrices will be shared by this diagonal matrix. It will have the same trace. It will have, I wrote down a lot of something, the things here. It has the same characteristic polynomial. That's the polynomial lambda I minus a equals 0. Right, the polynomial you get from that equation is called the characteristic polynomial. Invertibility. In the sense that you can now realize that an n by n matrix is invertible if and only if all its eigenvalues are non-zero. Right? That's one way you can describe an invertible matrix. And I'll be like a commercial, and much more, right? So the idea is these two matrices, D and A, will share a lot of the same properties, and you can even see some of them here. Like, where's A? What is the trace of A here?
-7.
What's the trace of this diagonal matrix? Right? Knowing the trace of one, I know the trace of the other. A lot of the properties will be the same. There will both be invertible or non-invertible at the same time. They'll have the same rank. The rank of this is 2, the rank of that is 2, and so on and so forth. They'll share a lot of the same properties. And since this is easier to deal with, I can study A indirectly by studying this guy. So if I need to do a bunch of things where I'm finding determinants and finding inverses and all that stuff, do it with this guy, and all the answers translate to this guy, right? So once I can diagonalize a matrix, it will greatly cut down on my computations and all the theoretical things I'm doing. So a lot of the theorems, why eigenvalues and eigenvectors are so important now, is that from this point on, a lot of the theorems you're dealing with in linear algebra, they can only show them, a lot of them, for diagonal matrices, because then once you know that corresponds to any other matrix, in the similar way, it will automatically apply. So we can study A by studying D in many cases, and that is very nice. A lot of our proofs will work out nicer, a lot of our computations will work out nicer. A lot of things just work out nicer. Oh, by the way, they have the same determinant. I don't know if I mentioned that. That's important as well. Right? Like all the stuff we've said was important before. They will share all these properties. Yeah, same rank, nullity, eigenvalues, eigenvectors, eigenspace dimensions, the basis, the determinant, the trace, the characteristic polynomials. They'll all be the same one to another. Here's another application. The powers of A. So let's look at this. Assume we can write A as a matrix times a diagonal times an invertible matrix. Let's say for some reason I want to multiply A by itself a whole bunch of times, which as we know can be very annoying. Right? Because it doesn't mean you just raise the power of each element, right? That's not true in general. It's true for diagonal matrices though. Maybe we can use that to our advantage. Right? So if you want to raise a matrix to a power, in general you can't just raise all the entries to the power. That would be incorrect. However, you can do that with a diagonal matrix. If you want to raise a diagonal matrix to a power, you can raise each individual entry to that power, and that's the answer. You don't have to do anything. Okay? So this is just A by itself, K times. Now assuming I can write A as that, what will happen? This means this is P times D, P inverse, times P times D, P inverse, times P times D, P inverse, times P times D, P inverse. You see something happening? All these intermediate P's will cancel out because I'm multiplying them by their inverses. And I would end up having P times D to the K, P inverse. So I can give you a 2 by 2 matrix and I can say, find A raised to the 100th power. Now you could multiply the matrix by itself 100 times, or you can just multiply these 3 matrices together. So they're useful in the sense that this matrix will share a lot of the same properties as A. It's also useful in the fact that if I want to find powers of A, so if I want to solve polynomial equations with matrices in them, it's easier to work with the diagonal matrix than it would be to work with an arbitrary matrix by itself. Assuming we can get here. So a lot of times if you want to solve some big linear algebra problem, first thing, check if it's diagonal. And if it is, it's probably better to work with the diagonal matrix. Right? Things will be a lot easier. So here's an example. Again, piggybacking on the last example. So let's say I gave you this guy, 5, 2, 2 minus 2. We know that A is equal to, what was the P? Minus 2, 1, 1, 2, minus 6, 0, 0, minus 1, times minus 2 over 5, 1 over 5, 1 over 5, 2 over 5. Therefore, this would imply if I want to find A raised to the 20th power, okay, I'm just calling a number, this is actually going to be equal to this times this to the 20th power. Now this guy to the 20th power, like, oh my god, now we have to raise that to the 20th power. No, that's just raising each individual term to the 20th power. So instead of multiplying that matrix by itself 20 times, I can just multiply 3 matrices together. Which, by the way, I wrote down what this is. You'll get something huge. This is 6 to the 20 plus 1 all over 5. 2 minus 2 times 6 to the 20 all over 5. This is 2 minus 2 times 6 to the 20 all over 5. This is 6 to the 20 plus 4 all over 5. And you can imagine what hell you would have gone through if you wanted to compute that directly. So if a matrix has n linearly independent eigenvectors, it is diagonalizable, meaning you can write it as something like this, where D is a diagonal matrix. In fact, we know the formulas for these. The guys on the diagonal will be the eigenvalues corresponding to each column here, and those columns come from the eigenvectors. Once you can do that, the matrix D and the matrix A will share a lot of the same properties. They'll have the same determinant, they'll have the same trace, they'll be invertible together or non-invertible together. They'll have the same eigenspace, eigenvalues, same characteristic polynomial, same everything. Not everything, a lot of things. As well as if I want to raise A to some arbitrarily large power, I can do that by raising the diagonal matrix to that power, which in the case of a diagonal matrix is stupidly trivial. You simply raise each entry to that power. Where are we? So I got another application. which is in 5.4. Systems of linear differential equations. Probably not all of you have taken differential equations, so let me just tell you. A differential equation, we have a whole class on this, but basically it's an equation that involves derivatives. Of the dependent variable. For example, back in Calc 1 or 2, depending on where you took it, you might have talked about a topic called exponential growth or compound interest or compounding continuously, and you looked at equations of this form. Y prime equals some constant times y. Right? So that was the growth rate of a, so if y was the current growth rate of a population, and you know it grows by k percentage points per year, then this equation will describe the rate of growth of the population at any time t. So something like that is called a differential equation. If the highest derivative is the first derivative and none of the y's are raised to powers or multiplying each other, the short for this is ODE. Stands for ordinary differential equation. The ODE is called a first order because it only goes up to the first derivative. Linear because all the powers are not, there are no powers greater than 1 and integers. Linear differential equation. So as a particular example, let me give you, so, for example, this equation give you a picture of it. So for example, if I look at something like this, here's the derivative of some value. I know that it is 5 minus 5 times that value plus 2 times some other value. Another quantity's derivative is 2 times some value minus 2 times some other value. So let's say I have two quantities that they're relating to each other. The rate of growth of one is affected by itself and the other, and the rate of growth of the second one is affected by itself and another. Right? So an application of something like this would be, okay, let's say we're dealing with two populations in the same ecosystem competing for resources. Then the growth rate of this guy depends on how many of them are there plus how many of the other guys are there, right? Because they're competing for the same resources amongst each other and with the other group, right? So you can have several differential equations kind of intermingling. In the case that none of the y's are raised to powers are multiplying each other, they're called linear differential equations. Since the first derivative is the highest derivative that appears, this is a first order linear differential equation, and this is a system of them. So we want to solve such systems. We know how to solve systems of linear equations, but when we throw derivatives into the mix, things kind of change a little bit. But problems like these arise all over. There are many applications to problems like these in engineering and science. So from like circuits and electronics and a lot of things have applications to equations like these. We want to solve it. So before that, let me mention some things, and then we'll piggyback on the same example to answer this. Okay. Let's give examples. Given y prime equals 3y, and y of 0 is equal to 5, solve this ODE. Okay? So just some ideas here. This guy is called the ODE. This guy is called the initial condition. As you might assume at some point, if I want to solve something, to solve means find the function that makes the ODE true. In other words, I want to find all functions such that when I take their first derivative, I get 3 times the original function. Okay? So that's what it means to solve an ODE. Get rid of the derivatives, pretty much. Solve for the dependent variable in such a way that no derivatives are present anymore. Okay? So here's a differential equation. I know an initial condition about the function. So I know the function I want to solve this. When I plug in 0, the output should be 5. And I want to find a function such that when I take its derivative, I get 3 times the original function. So this is one of the first kinds of equations you'll learn to solve in a differential equations class, but we're going to learn to solve it in a minute. Because, can you see a solution to this right away? Yeah?
Y equals e to the 3x plus 4.
No, the plus 4 is a problem.
How do you get?
So y is going to be e to the 3x. Okay? So this is the base solution. It turns out that any constant times this will work. Right? This is called the general solution. So this is a very important kind of differential equation. But it's solved by the exponential. So in differential equations, you will learn that solutions to things of that form is of that form. And there's something called the existence and uniqueness theorem, which I've actually mentioned many times before. So in other words, we know that's a solution, and you can prove that all solutions have to have that form. Is the upshot of it. To find a so-called particular solution, we must further solve so that if I take y of 0, the answer should be 5. So this means if I plug in 0 into x, I want the answer to be 5. This would mean that c equals 5. This would mean the guy I'm looking for, the particular guy I'm looking for, is 5e to the 3x. So this is a function that solves this equation, and that condition will work. Right? If I plug in 0 here, the output is 5. So this is what we call a homogeneous first order linear differential equation. and that has an initial condition. All guys of this form have that kind of solution, and we can solve for particular solutions by just plugging in these numbers and solving for the arbitrary constants. Now, note, we may write a system of such solutions as some vector that describes the derivatives, a matrix that describes all the coefficients, and some vector that describes those guys. Right? So, example, in the system I gave you, y1 prime is equal to minus 5y1 plus 2y2, and y2 prime equals 2y1 minus 2y2. I can write that using our idea from linear algebra. In the same way I write a system of regular linear equations in matrix form, I can write this in matrix form. So I can write y1 prime, y2 prime, and this would be equal to minus 5, 2, 2 minus 2 times y1, y2. In other words, I can write this as some vector that contains my derivatives. This is the matrix of coefficients, and this guy, I can just talk about that. So now to solve this, we need to find y. Spoiler, I'm going to tell you exactly how to find y. It's a well-known problem that we know the solution to, and another spoiler involves eigenvalues and eigenvectors. So here's a spoiler alert to this, is that y will have this form. It will be similar to the fact that the exponential always solves guys like this. Exponentials are going to be involved here. It is going to look like the eigenvector times the eigenvalue as the coefficient of E, plus the second eigenvector with the second eigenvalue in the power of the E. In fact, this works in general, by the way. If y prime times a y is an n by n system of linear ODEs, then the solution can always be written in terms of eigenvalues and eigenvectors. Y will be equal to the lambda 1 vector e to the lambda 1 times x plus the lambda 2 vector e to the lambda 2 times x plus all the way down to the lambda n vector e to the lambda n times x. So eigenvalues and eigenvectors are useful in solving equations like these, which if you've taken differential equations, you'd realize just how supremely important solving equations like these are. If you haven't taken differential equations, just take my word for it. It's super important to be able to solve equations like this. So let's actually go back to our main example. So here, solve y1 prime equals minus 5y1 plus 2y2, and y2 prime equals 2y1 minus 2y2. Here, notice that your A is going to be the same guy that we dealt with before, so we kind of know all the answers that come out of that. So you go through that process, so we know already that lambda 1 is minus 6, we know that lambda 2 is minus 1, we know that the corresponding vector here is minus 2, 1, corresponding vector here was 1, 2. I should have memorized by now. Yeah. So this implies, if you went through all the trouble to find that, you can actually know the answer right away. Your y will be equal to minus 2, 1, e to the minus 6x plus 1, 2, e to the minus x. Done. It's done because we actually did the work to find this. So finding the eigenvalues and eigenvectors are very important, and they have a lot of applications. We can solve linear ODEs, we can diagonalize matrices, we can do a whole bunch of stuff. So in other words, to flesh this out a little bit, this means that y1, y2 is equal to minus 2, well, technically there should be arbitrary constants here, minus 2, oh, and put in down here. You should have arbitrary constants on those guys. So go back and just write like a C1 in front of that, C2 in front of that. I'm rushing too much. Cn in front of this. Right, for the same reasons that I had the Ce to the 3x in the last example, because every constant times the solution will be a solution, because it's a vector space, which in differential equations they wouldn't have told you that, but that's why. So you put a constant here because a constant times any solution will also be a solution. And so you can say here, this is 2e to the minus 6x plus e to the plus c2 e to the minus x. And this one down here will be c1 e to the minus 6x plus 2c2 e to the minus x. So the constants, you won't know what they are until you're given information. We can find the c1 and c2 only if given some initial condition. I don't know if I gave an example though. I did. Okay, so we did a lot. So given some matrix, we can find its eigenvalues and eigenvectors by doing what we did before. So take lambda I minus this, find its determinant, set it equal to 0, solve for the solutions, that gives you the eigenvalues. For each of those values, plug it back into that equation and solve for the vector solutions, that gives you the eigenvectors. Once you have those, you can diagonalize the matrix as described before, and you can solve equations that look like this by just plugging into that formula. And you can also take this guy, raise to any powers using the other formula. So those are the three main applications that we care about, but there are many, many, many more. So yeah, so on the bonus and probably definitely on a question in the final, you can expect a question asking you all these things. Here's a matrix, find its eigenvalues and eigenvectors, diagonalize this matrix, use your answers to solve this system. And what is the matrix raised to the 100th power, some arbitrary power? And you should be able to answer all of those. Most of the work happens with you actually finding the eigenvalues and eigenvectors. The rest of it is just you plugging into formulas. And that's all we wanted to discuss. So that's the end of this course. So happy, so happy. Okay, so that's that. So the test is tomorrow. It'll look like what I told you before. So what we did today would be in the bonus section. So learn it if you can by tomorrow. If not, don't worry about it too much. Make sure you know all the other stuff. And we will stop there. Pretty much right on time.